Joining us today on Superheroes of Science, we're pleased to welcome Dimitrios Giannios, Associate Professor in the Department of Physics and Astronomy here at Purdue University. So welcome.
Hello, thanks for having me.
We appreciate you taking time to meet with us so we can interview you.
Mm-hmm.
And we were very excited. And say Sarah and I, when we were chatting about it, we were very excited.
Oh, yes. I think.
And you're going to have a little bit of explaining to do because I think when we start talking about your area of research, a lot of people will have either misconceptions or no idea exactly what that is.
Mm-hmm.
So do you want to start kind of explaining what you research? I can't remember how we started.
Okay, thank you. Thank you for giving me the opportunity to discuss my research with you. My work is on theoretical astrophysics. So we are here on Earth and we are wondering what happens out there in the universe. And we are looking at violent phenomena, at phenomena that have to do with deaths of stars, with explosions, with the formation of black holes and neutron stars and other exotic objects. And of course, we are so far away, we can get all this information just mainly, actually, just from the light that we receive from these objects. So it's really the electromagnetic radiation from these sources out there in the universe that we are learning about, the universe as a whole.
Now, when you say electromagnetic radiation, I think you were kind of going to explain a little bit more what we mean when we start talking about that?
Absolutely. And if I may share a screen with you so that okay, you get the picture, so I guess now we can share the screen. Here is a plot or a graph, if you wish, of the electromagnetic spectrum. Now, we call it in many different names, but it's one thing, it's light. Electromagnetic radiation is light, just like the light we see from the sun. At the same time, there are waves. It's oscillating electric and magnetic field. Many times we call it also photons because quantum mechanically waves and particles are the same, the two sides of the same coin. So you hear many names for this thing, but in reality it's just light. Now, the big difference is that our eyes are trained to see only a small, narrow range of this light. We can see the red, the green, up to the blue, the rainbow colors. But that's also only a narrow range. In reality, the light extends from radio to microwave, like in your microwave oven, to infrared, all the way to X-rays and gamma rays. And this is also light, but it is oscillating at different frequencies. So gamma rays is light that oscillates very fast. And when you have fast oscillations, you have short wavelengths. As you can see here in this plot, for example, let's go back here. Here at the gamma rays, you have short wavelengths and very high frequencies of oscillation. Now, what our eyes can see is this very narrow range of the spectrum, which has the colors that we all know. It is the red, the yellow, the green, the blue, the violet of the rainbow. But the spectrum extends at much wider range.
And so when we're talking about the different wavelengths, or do they call bands? Like in X-ray, is it a band, or is it just that wavelength? How do we say that? I don't want to say it wrong.
That is exact. So just so that we speak the same language, the astronomers, we decide, okay, a range of wavelengths of these waves to call them with a specific name. So there is the band of the X-rays, there is the band of gamma rays, ultraviolet, and so on. For the optical light, the light we can see with our eyes, we call it visual. Now, visual is what our sun produces and most of the stars are producing. And in fact, our eyes are trained because of the sunlight to be sensitive, to be able to see this light. Since the sun produces this light, our eyes evolved through evolution actually to look at this exactly wavelengths. But in fact, there are animals in the animal kingdom, for example, the snakes, that can look at the infrared. So they can look at the infrared, which are longer wavelengths, and can detect the heat of the bodies of small mammals. And that's how they do the hunting during the night. It's essentially like infrared cameras that they are using. So, for example, if you forget about the visual, you can think how the world, how the things around us would look like in the infrared. And these are the infrared cameras you are seeing here. This person here takes a photo of himself in the infrared, and you can see his head glowing even more because it's the heat generated because of his body. And you see his glasses are dark just because they're cooler, they're not touching his face. And you see this cute dog here, it is red just because of the heat of its body. So if you were a snake during the night, you could go and attack this dog just looking at the heat of its body. Furthermore, for example, here you can see the X-ray vision. We are all aware of X-rays because, okay, if we break something, we take our X-ray and we see the structure of our bones. The X-rays have the ability to penetrate through our skin and muscles, but they are blocked by the bones. So the X-rays actually take a picture of the structure of our bones. So it's the same hunt, but looking at it through the X-rays, it looks very different.
But I do want to make clear though, or I could be a misconception for me, but we don't have like in our phones, we can't actually do. I know it looks like it's almost a camera, a phone camera doing it, but we don't have technology who would actually take X-rays through like a camera or a phone, right?
That is correct. That's just to show that, in fact, using the X-rays, you can see the same object, a very different view of the same object. We have infrared cameras. We can look at the infrared, looking directly at the heat of the body. And that actually to make the point that the sun is very hot. It has a temperature of 6,000 degrees, and that results in the visual and the optical light. Our bodies are, of course, cooler at that 100 Fahrenheit. They produce different light, infrared light. Every object with some temperature produces light. The light from our bodies is in the infrared, and then you can use an infrared detector to see the light. That is the point here one can make, and that we exploit this a lot in astrophysics, because with different detectors, nowadays we don't only look at the optical light from the different objects, but we have satellites in orbit around the Earth to detect the sources in the X-rays, in the infrared, and in the gamma rays, for example. So looking at the same object at different wavelengths, we see something very different for this object. Just like these pictures here, looking at the different wavelengths, we get a very different information for these objects.
Oh, very nice.
So if I may continue, actually, I can directly tell you what we can learn from looking at different wavelengths at the same object. And here it's a very familiar object to everybody. And guess what it is, right? As the name here reveals, it's just our sun, right? It's the same object, and it looks so different in the different pictures. Why is that? Well, that is the sun that we all know and love, that is in the visible. And even if you notice, there is these dark spots that you see in the surface, and these are the sunspots of the sun. These are regions actually where there is activity. There are strong magnetic fields, and it's a bit cooler there. That's why it appears as dark in the optical. However, if you look at the sun at the radio or infrared, at different frequency of the radiation, you see very different picture. In fact, scientists realize that there is so much activity happening outside the surface of the sun. And you can see all these spectacular flares and hot spots, regions. It's much bigger now in size in other wavelengths. And this is only possible to study if you go beyond the optical light. That was possible actually only after the 50s, 1950s and 60s, when satellites made it outside Earth's atmosphere. The reason for this is that X-rays and gamma rays and all this radiation cannot penetrate the atmosphere of the Earth. It's blocked in the atmosphere. And that's good for life on Earth because we would be completely burned by X-rays and ultraviolet light from the sun, right? It would be very bad for us and very bad for life. But it's bad also not to be able to see the universe. So you have to make it outside the atmosphere to observe at these wavelengths.
And so are all of these, the pictures, the images I see on the screen, are those all being emitted from the sun itself then? So it's actually emitting X-rays and emitting infrared and radio and visible, and it's emitting those wavelengths?
Exactly. That is exactly. Most of the light we see from the sun comes from the optical, but there is emission in all these different wavelengths. In fact, these pictures are simultaneous. It's the same sun taking the same instant. This dark spot you see here actually corresponds to this bright spot in the infrared or to this bright spot in the X-rays. So you know that although it is darker in the optical light, there is more activity happening at other wavelengths. And that tells you something about how hot is the sun in this region and processes that take place in this particular dark spot here of the sun.
I know we can look at the sky and see the sun, but you had mentioned looking at like the formation of stars or the formation of black holes, or maybe you said the explosion of stars, but what's the time frame? Like when we get information or see light coming from stars that are really far away, how long does it take for stars that are really far away to get to us to see those?
Oh, yes. It's a bit of like archaeology. We are looking at the past, just looking at the night sky. Looking at a star that is in our own galaxy, we are looking at how the star was some 10 or 20 or 30,000 years ago. So light takes 30,000 years to travel from some place in our galaxy to us. So we are looking at the past. However, we see faraway galaxies and explosions that take place in a faraway galaxy. And then for the light, it could take millions or even billions of years to make it to us. We are looking at things that have happened maybe just after the birth of our own universe. We are looking deep into the past in many cases. Yeah.
Even with those waves, I mean, those same waves from all that time ago, they've made it this far so we can see it. That's
yes.
Hardly.
That's amazing. Our universe is transparent for radiation. The waves keep traveling forever in the universe. The challenge is that if you are looking at a faraway source, the waves get diluted. It spread more and more and more. So what you need is bigger and bigger detectors to get a very faint signal, a very faint detection of the source. So the further away, if I hold the lamp and I'm next to it, I can see it bright and clear. If I put it a mile away, it will get fairly faint. In these cases, as if I put the lamp somewhere to the moon and I try to look at it. So it's a similar situation where you try to get to see a tiny, very faint source that is very far away.
Now, are these other stars, are they emitting the same wave bands that you mentioned as our sun?
Yes, when we are looking at the stars, they are mainly emitting at the same wave bands. Some stars are a bit redder and some stars are a bit bluer, but overall they are emitting around the visual. And that was our naive picture of the universe when we had only optical telescopes. What is the galaxy or the universe? Is a collection of stars. Well, interesting because they are hosting and nurturing life on Earth, but they live for billions of years and not much changes, right? That was the picture about the universe. However, when we sent the satellites in orbit and looked at X-rays and gamma rays and infrared radiation, we found actually a completely new universe, completely new sources we hadn't imagined. And these are sources that are changing all the time. They are varying their light. You see explosions and things that change all the time. And these are just some pictures of these discoveries that took place only the last few decades. In X-rays and the infrared, we saw pulsars. These are rotating neutron stars. Neutron stars and black holes, to back up a bit, are the end point of the death of very big stars. When a star has lived its life for millions or billions of years, finally it collapses, it runs out of fuel, cannot anymore resist its own gravity, and collapses to a compact object that can be a black hole or a neutron star. And these neutron stars are really dense objects. You take the mass of the sun, or twice the mass of the sun, you shrink it to something of the size of the broader Lafayette area. That's the size, is around 6 miles, the size of a neutron star, and its density is absolutely enormous. You can imagine let's calculate, it's a million billion times denser than water. Okay, so it's very, very dense object. Black holes are even more compact, and from black holes, not even light can escape. These are predictions from Einstein's theory of relativity, and now they have been directly observed with these very powerful telescopes.
Wow, how does particles compact that tight to be so dense?
Yeah, so in fact, the neutron star looks like a huge nucleus. So you have your atoms, and your atoms have the nucleus and the electrons rotating around in the nucleus. Now, in normal matter, the space between the nuclei is vast. The nucleus is tiny, and then the space is very large. There is a lot of empty space. Now, when the neutron stars are forming, you pack things so close together that the nuclei are touching each other. So essentially, the whole neutron star, you can think of it as a huge nucleus. It has the density of nuclear matter. The whole star is as dense as the nucleus of, for example, uranium nucleus.
Wow.
These are extreme objects. As I said, they can be 6 miles across. They can spin faster than our bladders. They can spin 1,000 times per second, and they are sending to us fast pulses of radiation. In that case, we call them pulsars. And this is exactly the picture of one of these pulsars. It formed actually at the year 1054. We know even the year when this neutron star was born. And the reason is that Chinese astronomers recorded the supernova at that year in the specific location of the sky. Now, modern astronomers realized that we see here the neutron star that came out of this historically recorded supernova.
Oh, so I mean, wow, because I would have thought the time it would take to record something like that would be like, it would take 1 billion years for it to happen. And so are these events that do not take as long to happen as I would have thought?
That is the exciting part. You can have a star, it can live quietly for millions of years, like a normal star, but once it runs out of fuel, it cannot burn anymore, then everything can happen very, very fast. In fact, it just takes a few seconds or minutes for the collapse of the star to a neutron star, and then within 1 hour or so, you get the supernova explosion. The light from the supernova is very bright. It lasts for months. So in fact, this specific supernova is believed that was visible in daytime for a few months. It was so bright, you could see it even at daytime until it fainted away. What is left behind is this structure here. It's a faint object that we still see around 1,000 years after its explosion.
Holy moly. And we only know this because we have, I want to say, special cameras out in space outside of our atmosphere that can record at those wavelengths outside of the visible. And that's how we know this.
Yes, absolutely. Just with the visible light, with the telescopes, we cannot get so much information about this specific objects, but the satellites in orbit look at the whole sky, take pictures, and focus on these interesting sources, and they study them in detail. Here, if you want, I can discuss one more source of interest. You see this black cycle here and this bright dot over there. That's actually an actual picture, an actual observation at radio wavelengths of the silhouette of a black hole. So now this is a big black hole at the center of a nearby galaxy. And normally you would think that black hole, well, it's black, it's not supposed to produce any light. But what we see shining here is a hot gas that falls into the black hole. While gas approaches the black hole, gets very hot and very shiny before it crosses the horizon of the black hole, the point of no return, after which you cannot see any light. So with these extremely nice, strong telescopes in the radio wavelengths, you can essentially take these tiny objects on the sky, amplify it in size, and see what is happening over there. These are very, very challenging observations. The size of this on the sky is like taking a coin, I don't know, a quarter, put it on the moon, and you try to see the size of this quarter on the moon. That's the size of this black hole in this galaxy, as seen from Earth, of course.
Oh, wow. And
how long does it take to find something like that? I mean, this is a really nice picture. Like, how long did it take someone to discover? Or is it just kind of by chance? Or
yeah,
things you know what you're looking for?
Right. We knew more or less where to look for it. And that is what happens at very much larger scales of this object. There are all this hot gas that is leaving the center of a galaxy, moving on this straight line. So astronomers for quite some time believed that there is something very interesting happening at the very heart, at the beginning of this object, which was exactly at the center of a galaxy. They knew that there is a large black hole being somewhere there. But to be able to take the photo of the black hole, you had to spread radio telescopes all around the Earth and devote a lot of time. It took several decades of effort of this collaboration to make this picture.
oh, wow. So do countries all over the Earth, are they I mean, when we say astrophysics, I guess we never really totally defined what astrophysics was. And so I have two questions for you. One, what exactly do we mean when we say astrophysics? And two, are there countries and scientists all over the world that collaborate to find out what's happening outside of the world? So two questions.
Yes, sure. Astrophysics is anything that is happening beyond our solar system. So there are fields of physics that have to do with the Earth or the solar system, which we could call, for example, solar physics. But then moving beyond our solar system, anything else, even cosmology and the universe as a whole, is a part of astrophysics and cosmology. Now, the second question was about the collaboration. Right, this observation required the radio detectors to be placed as far apart as possible to make very detailed observation of this object. So in fact, this photo required detectors in Hawaii, a few of them in continental US, Latin America, Antarctica, Canary Islands, Europe, and so on and so forth. You had to spread them as wide as possible. So you have to go from Antarctica all the way to Arizona, for example.
Wow.
Wow.
What benefit with this many different places and people were willing to collaborate to discover this knowledge, what is the benefit to people? What uh, other than I mean, I'm assuming just understanding the unknown, but what benefit do other benefits are people seeing with this?
So these observations are testing our understanding of physics to the extreme. When Albert Einstein wrote down his equation for the general theory of relativity, then which is describing how gravity works, and in fact is an important theory with many practical applications. Although it seems so remote and so strange, in fact, just the GPS application, the global positioning system, cannot work without the knowledge of general theory of relativity. You have to correct for the general theory of relativity to have it working. But moreover, when he wrote down his equations, people soon after him realized that there are some strange solutions of his equations, giving birth to exotic objects like black holes. So the ultimate test of his theory comes from testing, looking for these objects and testing his theory to the extreme. As you said, it's more like a conceptual battle we are having all the time, trying to push our knowledge to the new extremes and try to see, actually we are looking forward for a point where our theories are breaking down. In physics, we like actually when we fail. We like when our theories are failing because then it's the new opportunity to learn something new. So we like to push the theories and looking forward to any failure of the theory.
Oh, I like that. I like that.
Yeah.
Now, it's like you had the pictures of different pictures of our sun at different wavelengths, and so you showed us X-ray, infrared, visible, and so this was taken at the same time. Are all of these different wave bands traveling through space at the same speed, or do they arrive at a spot staggered?
Yeah, that's a good question. Light, independently of its wavelength, travels exactly at the same speed, the speed of light, which is 300,000 kilometers per second. To say it in other words, it takes approximately 1 second for light to arrive from the moon to us. So the moon is 1 light second away from us, if you wish, in these astronomical units. The sun is 8 minutes away from us, which means that the light takes approximately 8 minutes to travel from the sun to us. And this is correct for all the different wavelengths. The same for X-rays, optical, or radio wavelengths. That was predicted by Maxwell's equations that describe light, electromagnetic radiation, and it's indeed verified. To that, I want to add that all the information we get about the universe nowadays is not coming only from light. The last 5-10 years or so, we have opened new windows to look at the universe. And that is thanks to neutrinos, which are very weakly interacting particles, thanks to gravitational waves, which are ripples of space and time, which also propagate, which also travel at the speed of light. And finally, that's because of cosmic rays, which are charged particles of very high energy that arrive on Earth, hit the atmosphere of Earth. All of these different messengers teach us about the universe, together with the electromagnetic radiation.
See, and that's amazing. We went from years ago to just having visible light to be able to, then you found all these wavelengths that you're able to search, and now you're finding things beyond those, being the particles and gravitational waves. What do you predict is that, let's say, I don't know, 100 years from now, what types of things do you think that we'll be using to understand the beyond our universe here?
Now, that's such a good question. Right now, and in the next decades, what we are trying to do is to combine the information of the different messengers, right? So, for example, a few years ago was the first discovery of gravitational waves and light at the same time from the same source. It was two neutron stars rotating around each other. They were producing gravitational waves, and when they smashed against each other, like in this picture here, they produce a flash of gamma rays and other wavelengths, light from other wavelengths as well. So now, for the first time, we can combine information from different sources, or different types of waves. Now, in the distant future, of course, it's out there. Hopefully, I cannot predict anything about this because it will be completely crazy. But just listening or measuring gravitational waves, you can learn about more violent things that may be happening in the universe, like exotic objects that we are only speculating now, like cosmic strings and some topological, let's say, artifacts that you may have in the universe. All these exotic objects, maybe we can start detecting them directly with, for example, gravitational waves.
Yeah, that's pretty cool. And it just amazes me when I first saw these, like the pictures you're showing now. To be honest, I assumed they were like an artist rendering of what we thought was happening. I didn't realize when I first started seeing these that, oh, these are actual images that were taken out there in space. And I think that's just amazing that we have technology to be able to record what's happening.
Yeah, absolutely. Yes, the technology has made it there where we can in fact just see directly the silhouette of a black hole. Of course, to be honest, this is still artistic rendering here. The smashing neutron stars, we didn't see the neutron stars smashing. It's just still too small of an object to detect them directly. Although in gravitational waves, you could see the frequency of two neutron stars coming, rotating around each other to increase as they were coming closer and closer and closer together, and then the signal disappeared the moment that they touched each other and became one object. So that was a very spectacular detection there.
Oh, I would think. What all right, so I think this is amazing, and I'm sure I'm not the only one. So what advice would you give students that were like, oh, I totally want to look into this. I want to learn this and be able to do this for a career down the road. What advice do you have them to for students who would like to get into this?
Yeah, it is an exciting field. There are many things happening right now. A few days or a month ago, they gave the Nobel Prize of Physics in the discovery and research related to black holes. And 4 years ago, they gave another Nobel Prize in Physics for the gravitational waves related again to collisions of black holes. So the field is very exciting and very fast developing and offers many new possibilities for graduate students. In fact, the first picture of a black hole and the software that was written to analyze this type of data that came to make this picture was from a graduate student. She was going there, writing the programs, doing the analysis. It took a graduate student with a lot of computer science and data analysis techniques to make such a picture. That is to say that fresh minds can come now and make a difference in the field because the field itself is fast evolving. It's a lot about big data. It's of course about physics, but it's also a lot about new data analysis techniques that are entering these fields.
So I like the fact you bring up the big data, and I imagine the data sets that you guys have to be able to go through is just inconceivable.
Enormous, yeah.
Absolutely. Nowadays, there are these surveys. We are looking at the night sky with a telescope, and we are receiving many terabytes of data every night, and you are looking for things in the sky that are changing. And obviously you cannot go by eye and look all these billions of sources out there. You have to write very smart software that are identifying automatically anything that is changing in the night sky, night after night after night.
Oh, see, there you go. You go into programming and then try to figure out what happened in the universe a million years ago.
So we are trying both to simulate the universe. Our work in my group is theoretical. We do computer simulations of the fluids that participate in these explosions, but this comes hand in hand with observations where they get all this data and analyze all this data for the observations of these objects.
And what do you mean by the fluids that are in part of this?
So here, what we see as shining is very hot plasma. Plasma is another, it's the fourth state of material. It's very hot fluid where the electrons are not anymore nicely rotating around the nuclei, but it's so hot that it's just a soup of free electrons and nuclei in these fluids. So we are solving for the equations of magnetized fluids, trying to understand how the plasma is heated and how it produces light. These simulations have to include the special theory of relativity. This material may be moving with a speed very close to the speed of light, and you have to account for the general theory of relativity, meaning that the space-time is curved, so you have to consider the motion of this fluid in curved space-time.
Oh, that's cool. This, Mercy. Well, thank you. This will fit into so many areas, and I think it's so amazing of a field itself. And I'm really excited that we got to talk to you about it and learn just a little bit more about understanding the universe behind us.
Absolutely, it's my pleasure. And yes, once we get another chance, I'm happy to be back and discuss some more for any of these topics, for example, gravitational waves or neutrinos, all these different messengers that we are using to explore the universe.